everyone. We're going to use the principle of mathematical induction to prove that the sum of 2i from 1 to n equals n squared plus n. And to use mathematical induction, there's the 3 steps that I call it: show, assume, and prove. Now, this is for all positive integers. So this is n, all positive integers. Also, for this summation notation, let's just look at what this is. These are positive numbers. So if you start with 1, 2 times 1 is 2, and then 2 times 2 is 4, and then go to 3, you get 6, and you get all the positive integers, or the even numbers. And then we'd have your last term would be n, so this would be 2n equals n squared plus n. So that makes it a little easier to look at that way. So now let's do our steps for principle of mathematical induction. So the first thing we want to do is show that it works for n equals 1. So if you plug in 1, like we already did that, plug in 1, you get 2 times 1 equals 1 squared plus 1. And that is 2 equals 2, so that checks out. The next thing you want to do is assume it works for n equals k. So what I'm going to do is take what I wrote out earlier and write everything. Every single n is going to have a k. So what we had was 2 plus 4 plus 6 plus dot, dot, dot. And we had 2n, so we're going to write 2k equals k squared plus k. Now, so all I did was do the same thing but copy that down. The next thing I'm going to do is prove that it works for the next term. So that means for the next term after k plus 1. So for example, if I said prove for n equals 2, well, if I plug in 2 in here, I get 4 plus 2 is 6, and I add these first two terms, and you get 6. So if I go for n equals 3, I'll get 9 plus 3. If I plug in 3, I get 9. 3 squared is 9 plus 3 is 12. And if I add the first 3 terms, because n is 3, that means your number of terms, that's going to give you 12, which it does. So we're just going to prove that no matter how many numbers you put in there, it works for the next one. So I'll just erase this. All right. Now, to do that, we're going to check for k plus 1. So you take this and copy it down. So we're going to write 2 plus 4 plus 6 plus dot, dot, dot plus 2k. So I just copied this whole thing down. Now the next term is going to be 2k plus 2. All right, and this one, we're just going to, everywhere there's a k, instead of k now, we're going to put k plus 1. All right, so this one right here, I just want to go over real quick. There's 2 ways to get this. You can either take your previous term, take that k, like we did here, and plug in k plus 1. And that gives you your k plus 2. Or you can see that this is a linear, since it's arithmetic, it's linear, and see the slope is 2. So if you have 2k plus 0 and add 2, you would get 2k plus 2. Or the next one would be 2k plus 4. The next one would be 2k plus 6. So you keep adding this slope to the term because you're going by 2's. But anyway, either way, we do that. Now, let's prove this by simplifying this. This right here we already know what this equals. That's why you have to copy this thing down. It equals k squared plus k. So you put k squared plus k. Now let's add the 2k plus 2. And you simplify this, you're going to get k squared plus 3k plus 2. Alright, now on this side's going to have to be simplified as well. So I'm going to FOIL that out. This is going to give me k squared plus 2k plus 1. And then we have plus k plus 1. And simplifying that gives us k squared plus these two add up to 3k. And these two ones add up to 2. So the right-hand side, or the left-hand side, equals the right-hand side. And we did our proof. Some people do that. All right. That's it. Thank you. Have a nice day. Bye-bye.